Hello, this is checkpoint 3.16. Let's take a look at a projectile problem where we have to shoot an arrow and we want to find out how far it goes. So generally we're going to shoot an arrow, and because of gravity it'll eventually land somewhere. And if we set this up as the x-axis and then this is the y-axis, we got ourselves a projectile problem that's dependent on some gravity. And and so when we get things set up, we just want to start off with our gravity, our acceleration due to gravity. And this is going to be just a pulling down, so there's nothing in the x component. And then there's we're doing this in centimeters, meters. So this is going to be 9.8. Let's say negative 9.8 meters per second squared. Okay. All right. Now to do this problem, we're going to need to get a few things set up. We know that from the horizontal, the angle of inclination of your initial vector is 40 degrees. And so that will give us a hint as to how to describe our initial velocity. We'll call it V naught. And if you remember, it has to do with the sine and cosine. So it's going to be the speed, which I believe was 98 meters per second. 98 times the cosine of the angle of inclination, and then 98 times the sine of the angle of inclination, and this is in meters per second. That is our initial velocity. Our initial position is the height, and our height is 171.5 centimeters. And we'll still say that our initial condition or initial position is not anywhere along the x-axis, so we'll call it 0. And then we have 171.5 centimeters. This is in centimeters, and we want things in meters. So I think we multiply this by 100. And if we divide by 100, and I think that's going to move the decimal place twice to the left. So it'll be 1.715, and then now we're in meters. And so now we're consistent with everything else. Okay. I think with that we should be ready to go. We have our acceleration given. We'll find our velocity function by integrating. So the integral of 0 is not 0. It's going to be a constant. And we're going to have a lot of constants flying around. So let's call this C sub 1. And we integrate negative 9.8. Get negative 9.8 t. And then another constant. So this is our second constant. And then what we want to do is we want to set this, set the t equal to 0, and then set that equal to the initial velocity, because that's what happens when t is equal to 0. So if you do that, you essentially get C1 is going to be equal to the first component, and C2, because when t is equal to 0, this thing disappears, and it'll just be C2 equal to 98 times sine 40. So let's keep those values. 98 times cosine of 40 degrees, comma, negative 98 t plus 98 sine of 40 degrees. Yeah, we can find decimals for them now, or let's just work with what we have and put the decimals in later. All right, our next step is to find the position function, r of t, and again we're going to integrate. And so we'll integrate this first component. You get 98 times cosine of 40 degrees times t plus another constant, let's call it C3. And then we'll integrate this again. So 9.8t, this is a point 9.8. So half of that, because we're going to have t squared over 2, half of that is negative 4.9 t squared plus 98 sine of 40 degrees times t, and then plus C4, our other constant. All right, it looks like, again, when we let t is equal to 0, this is going to be equal to the initial position. And when t is equal to 0, it's just going to be constant. So C3 will equal to 0, and C4 will equal to the component here, which is 1.715. So our actual position function is 98 times cosine of 40 degrees times t plus 0, and negative 4.9 t squared plus 98 sine of 40 degrees times t plus our constant, or our initial height, 1.715. Okay, so that's our position function. Now let's answer the question of when it's going to land and then how far it's going to land. So we want this distance over here. This is actually the y component of some time, and the time where it ends. So I think we need to find out where it ends first, and we'll do that. That happens t end. That happens when the y component of your position function is equal to 0. So let's see if we can find that. We're going to set this equal to 0. Negative 4.9 t squared plus 98 sine of 40 degrees times t plus 1.715. Set that equal to 0. I did this work already, and it's just some calculator work or computer work that you can do. We got two values. I got negative 0.027 seconds for the first one, which clearly is not going to happen. That's this point over here. That's the time over there, and it'll be on the negative side. But the answer that we're looking for is 12.8829, and this is the time in seconds that we want. So that's the time that the arrow is going to take in the air until it lands. And once we get the place, the time when it lands, then we figure out what y of this number that we just found is. Or I guess we want the x value of that. So sorry, this is an x value. And we basically put this into this formula. So we get 98 times cosine of 40 degrees times the t value that we just found, t sub end, which is 12.8829. And I put that in the calculator, and it looks like I get 967.151, and this is going to be in meters. Okay, let's say meters over here since it got cut out. All right, that's your projectile problem. Good luck.